Good evening, everyone. We are about to begin. As I can see, almost everyone is here. Some of you are still not. Okay. So hopefully they will be joining soon. So today I will be doing it with respect to linear algebra section. In the last class we have done the integral calculus and the applications on that. So today's my focus will be on this, and alongside with this, I will also be working in the upcoming sessions on modern algebra as well. Okay, so where we will be doing different kind of stuff. So while the session is going on, so today is a brief recapitulatory session, we can say. So many new things, many old things all together will be done. So a conceptual roundup will also be the forte in today's session. While the session is going on, you can ask me anything on WhatsApp at 98367 93076. Let me open just the code. Okay, so here we go. So main focus, okay, the phone number which you have asked is 98367 93076. And after the end of the session, whatever will be done on board, so that will be shared as a PDF with you. So if you miss out writing something, then also it's okay. Don't worry about that. So that will be shared, and the entire classes recording will also be given. Okay. So in why we are going for a linear algebra roundup, you will understand soon, because this linear algebra roundup we won't be able to go to the modern algebra structure as well. Okay, so an assimilatory way we will be doing. First of all, can anyone tell me what is the difference between a matrix and a determinant? Okay, and remember that I need an adult answer, not like the first class 11 12ish answer. Okay, so is what is the main difference between the two with respect to a formational analysis in advanced linear algebra? What do you think? Or yeah, tell me.
सर डिटर्मिनेंट इज ऑलवेज अ स्क्वायर मैट्रिक्स एंड एंड में जाके उसकी एक वैल्यू निकलती है अनलाइक मैट्रिसेस.
Yeah. So this is what you said is a characteristic. So characteristic we can say many things. Okay, so for like matrices may not be a square, determinant has to be a n into n format. There has to be a value, it is not a value structure. So it can be represented a matrix, maybe a juxtaposition of the determinant, but determinant can not be all the times a reverse mechanism. So all these things are characteristics. Okay, and definition wise also we know. So my point is here when we are trying to find the difference at this level. Okay, so because we know about the varieties, different kind of Hamiltonian form and juxt form and non-linear, linear, everything we have done with respect to matrix, but determinant has very less applications anyway. Okay, so with respect to these parts, I'm not asking what is the difference. I said that with respect to formation analysis, what's the difference? Okay, because that is the key here. Anyone else want to give it a try? Or you can again? Okay, let's see this thing. So whenever we have why we needed this thing, this is not only a normal mathematical formation. So when we have a system and we do not know about the system, so it's a not a predetermined system. Okay, not everything is fixed up. Okay, for example, if it is a input output system, input and output structure, then it is easy. So in case of an input and output system, so it is fixed. So A1 is the input and B1 is the B1, B2, B3. In that way, A2, A3. So either you can go from this to this to this. So this is a format is fixed. Okay. So there will be a 9 possibilities with respect to these segmentation. So A1 with B1, A1 with B2, so A2 with B1, A2 with B3, A3 with B3, A3 with B1. So it's predetermined system. But when we don't have the luxury of knowing the system beforehand, then comes the concept of matrix. So, which is the real life format of forming a matrix as well. So, every time, whenever this calculative process is coming in front of us, हमें क्या लगता है कि हमारे पास ये पहले से प्री डिटरमाइंड स्ट्रक्चर है ही नहीं, तब हम लोग एक मैट्रिक्स का फॉर्मेशन देते हैं. वो एक हैमिल्टोनियन के रूप में आ सकता है, वो एक नॉर्मल स्ट्रक्चर रूप में आ सकता है, या फिर वो ऐसे कुछ रूप में भी आ सकता है जिसमें मान लीजिए हम एक पैटर्न को लेके इनफाइनाइट फॉर्मेशंस भी पढ़ सकते हैं. फॉर एग्जांपल व्हाट हैपेंस विद A1 gives a formation with B1, B2, B3, B4, B5, B6 dot B20 billion. So this also be a matrix, right? So 1 into 20 billion matrix. So that can be a formation, isn't it? So it's just like this. For example, when we are not predetermined with the structure and we wanted to expand it to any level, we take the help of matrices. So that is the expected outcome every time. We don't know. For example, we are finding that y is dependent on x1. But when we see all the values of x1, we still can't predict it. So we add another one, x2. Then we see here another one, x4. In that way, how many variables actually can predict everything, we don't know. For example, our face. Okay? Our face is a perfect example of a matrix. Now, how can a face can be an example of a matrix? For example, if you see my face, you can guess my age, right? If I see your age, I can guess your age. If you see my father's face, you can guess his age. Okay, so the face, by face, we can guess the age. But remember that if you see those Redmi cameras, Redmi phones, those you have, they, whenever you try to take a selfie, they try to guess your age. Sometimes it is wrong, sometimes it is right. Okay, so now this face camera guessing the age is dependent on many factors like the eyes, like the drooping part, the skin toning. So many variables are there, and altogether they are deciding that what will be your age. What is the exact value? For example, even a bad skin of a person who is only 18-year-old, will he look younger to a person who is very good skin but at 40 years old? I don't think so, except some special extreme cases. See, so our face and our mind can read all the infinite number. Here it's finite actually. So, but we don't know the exact amount. So we need to make it as an expandable format. So that's why today's discussion about matrix and determinants of the linear algebra will be a little bit different format. I will try to introduce. Okay. So till now, any problem? So remember that it gives you, it allows you to expand your wings. Okay. And how much big you can become, how much is the spectrum, or how much larger the spectrum is, it allows you to do that. Okay, so now there are normal multiplication structures and all these things. What is the triangular matrix, upper triangular, lower triangular? I hope you know these parts. Okay, so I will only be concentrating on now those things which are relatively non-usual ones. Let me just do one thing. Yeah, some special type of matrices. Have you heard about, obviously you guys heard about, a nilpotent matrix? There is no problem for this. Nilpotent is what? A to the power k equal to 0. Now what is the restriction on k? Any positive and integer. These are the two restrictions on k. Okay. But if I change a little bit, Can you find the index from this? What is the index of the matrix? If the Nilpotent matrix is A to the power k equal to 0. Or rather say, in examination, in ISI 1 they asked, what is the nilpotency index? For many of the students, it was a very new term. Anyone know what is the nilpotency index? Give it a try.
The smallest integer k that takes this that it works for
The smallest integer value.
of k.
Yeah. Remember that smallest value of k can do, because k we have already given it as a positive integer. So the least possible value. Now this we will discuss again. So if we are getting a 0, then what is the point of doing it? Then comes the concept of periodicity. Periodicity tells you that a to the power k plus 1 equal to a, then positive integer k, so that is called the period of k, period of the matrix. So after certain things, it will be repeated. Okay. So now period can be, for example, a4 may be a, then maybe a7, maybe this, maybe a10, maybe this, maybe a13, 16 in that way. Okay. Now, if I tell you that, can periodicity leads to nilpotency anywhere? Is it possible? Any idea? Is there any connection? For example, you see that it is only applicable if the matrice's determinant value is 0. In that case, obviously, it's useless to say. For example, what happens if we have it like this? A square equal to 0. Okay. Or if I have it a to the power 10 equal to 0. So both are giving 0, but the nilpotency index of the second matrix is higher. Okay. So you need to go for this matrix if you want to end up having a 0. Remember that in earlier mathematicians who, before the innovation of 0, mathematical equations were very hard to solve, because how an equation is solved? F of x equal to 0, just solve it with respect to the power, isn't it? That's the way computers also solve. So computer also uses the concept of binary. Okay, so the binary concept would not have been come with respect to, so there is a lot of different kind of discussions on this. So in an equation format, the RHS is determined with respect to a nullness. Okay, nil. So otherwise we cannot reach to that. We will keep on coming to these factors a little bit later on, but let me just give you a reminder on the Hermitian and skew-Hermitian. Hermitian, if you don't get it, you can interrupt me and ask me again. Okay, because these things are not very easy if you have forgotten. So Hermitian and skew-Hermitian. So if you, it reminds me of one thing, if it is reminds you as well, then it's very common, that is symmetric and skew symmetric. Okay, it is exactly like that only, only a little bit difference. We call it Aij. Equal to Aj. That's it, for all I equal to j. That is, we call it a to the power theta equal to. So for example, we can say it for an Hermitian matrix. This is a Hermitian. And if I have a skew-Hermitian,
So this complex number term is also called this Hermitian matrix.
yeah. It has to be with respect to the square matrix called a Hermitian if this format is there. So complex thing has to be there. Okay. Remember that if you think that complex numbers say real numbers has come, it's not that thing. Actually, real is a subset of complex, a plus ib. So this is a complex number, this is the real part, and this is the complex part. Okay, so whole thing, it is making it the whole thing complex. So if we're taking a complex number, so we are taking the real number all the time. We can drop this part, but we cannot drop this part. So here in skew-Hermitian, is just the difference is this 3 plus 2i and 4 plus I and 2i minus 6i minus 2 plus I. So this should be minus 3 plus 2i and 2 plus I. So I think you got that change. So this time Aji equal to minus, sorry, Aij equal to minus Aji. Okay. You see that here there is no restriction on this part, and here this has to be complex again. If it is minus 4 plus this, so the complex part is not changing, only real part sign is changing. This real part sign is changing, this real part sign is changing. If I show it by two different colors, this with this with this, and this with this. Clear? Here also we can show it in this way, but here the sign changes are happening with respect to the imaginary part, and here happening with respect to the real part. And in the yellow one, actually there is no real part I have written. For example, 4 minus 2i, 4 plus 2i, in that way also we can adjust it. Got it? So this is the skew-Hermitian structure. Now we will be using this kind of stuff in the upcoming part. Okay, so when we will working on the many types of symmetricity of a matrix. Now, what is a symmetry? So with respect to our lives, we can see a symmetry into human body. So human body is having a, what kind of symmetry? Is it symmetry number 1 or symmetry number 2? It's a vertical symmetry. We have it in human body, isn't it? So if it is a human body, okay, so this is exactly the vertical symmetry which we are talking about. The horizontal symmetry is not at all applicable. Okay. Now, here in matrices also, there will be very advanced level of symmetries will be there. Derivative of a determinant we did there, okay, with respect to utilization of a lot of properties. So here also similar kind of things will be there. I will also be focusing on the sums, but not today. Today I will be focusing on the theoretical part. Okay. One of the biggest, easiest, toughest, hardest, whatever it is, okay. Bhuvi, first your answer is how to find the conjugate. Okay. I'm coming to that. Okay. Next, one of you, another send me a question. Unable to join the class. Oh, come on. Every day same thing happens. Let me just see. Just give me a second, guys. Okay. One of you got a question here, name not written. If we take different level, okay, level based value I will coming in the echelon formation, don't worry. Where was I? Yeah. For example, in echelon formation. So what is an echelon matrix? I know most of you are very much Riddhi, again you missed out today and you haven't got it. What's happening? Every day you are missing out, so I think you have not saved that number properly. The 9674 number which I have given. This class also you are joining too late. Okay, so what is the echelon formation? And before that, when can we use this for two matrices? The equivalency relation. So if matrix A somehow can give or produce matrix B, or somehow B to A can be produced. So this is called the equivalency of the matrices. So what is this echelon form? Let me just say it. Let me just write one thing. 0, 1, 3, as complex as possible I'm writing. Then 0, 0, 0, 1, 0, minus 3, 0, 4 zeros, 1 minus 2 and 0. Okay. First of all, each leading non-zero entry is 1. Okay. So if you start with a 0, so the zeros has to be increasing. But remember that this is only applicable to these connected zeros. This has 1, this has 3, this has 4, this has 6. These are connected. So each leading non-zero entry is the only non-zero entry in that column. Okay. Each non-zero entry is the only non-zero entry in that column. Okay. So this is very, very important about a formation. So if these zeros are useless. Okay. If I have a perfect form 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. So this is a perfect formation, isn't it? Classy yet effective. Now, how to find the trace of the matrix? Now, can anyone tell me what is this trace? We know how to find the trace of all, finding the determinant also, and by this echelon form. But what is this trace? Normally, sum of the principal diagonal elements, isn't it, of a matrix? So why we need that anyway? Why we need a trace of a matrix? Because we need to judge that whether this matrix is at all usable or not. This is not applicable for a small matrix, for example 17 to 92 matrices. So in that case, so you take the principal 17 to 70 matrix, let us say. So you take the principal diagonal sum and check it and compare with another one. And if you have like 50 or 60 matrices like this, so how quickly you can form it? So that's why trace comes handy. Okay. Now, how to do that ranking of a matrix, rank of a matrix. So this is the most key. So here number of non-zero rows. Okay, what is a zero row? If all the elements are 0, then only it's a 0 row. So what is the rank here? 4, isn't it? We will be telling a lot of rules on this. Now, one rule about a matrix is, in generally, rank is represented by this row thing. Okay. So row equal to number of non-zero rows in a row echelon form we have done. So row of A, row of B minus n of minus n less than equal to row of AB less than equal to minimum of row A comma row B. This is very important. Where A and B are the square matrices, AB are square matrices are order n. Here. So this is a very crucial thing in MCQs. You will find it at least once in every examination. Okay. So row A plus row B means rank of A plus rank of B minus n less than equal to rank of AB less than equal to minimum of this two. Okay. Till now, any questions? Now, what happens if I multiply a matrix with respect to a non-singular matrix? You might multiply a matrix with respect to a non-singular one. So, will there be a change in rank? Yes or no? Answer is no. The matrix does not alter. The rank will not change. Okay. Next. Another thing I will be introducing today. Okay. What is nullity of a matrix? Let mn m into n is a matrix. Okay. And rank of the matrix is r, small r. Okay. So nullity is n minus r. Remember that m into n say row into column. So I could have said column minus rank. That is the nullity of a matrix in easiest of the formation. So how can we say 1, 2, 3, 1, 4, 2, 2, 6, 5? What is the nullity of this thing? What is the rank of this matrix? It's 1, 2, 3, and R2 minus R1 we can say. R2 minus R1 करने से क्या हो जाएगा? पहला 0 आ गया हम लोगों के पास 0, 2 and minus 1. फिर करेंगे R3 minus 2 R1. So यहाँ भी 0, 2 and minus 1. Okay, so this is the matrix now. So this is again the A matrix itself. So what is the rank of the matrix? 3. What's the determinant से भी निकाल सकते थे, कोई problem नहीं है. नहीं 3 शायद नहीं है. I think yeah. If we do another calculation, it will be reduced to another, I think. 1, 2, 3, 0, 2 minus 1, 0 says 0, 2, 2 minus 2 is 0, and 0. So rank is 2, isn't it? So rank of the matrix is 2. So what is the nullity of the matrix? Any idea? 3 minus 2. So nullity equal to 1. So there isn't any problem of finding the nullity in these cases. In bigger matrices also we can find it. And anyway, it has nothing to do with the squareness of a matrix. In a non-square cases also you can find it.
So column minus rank is equal to nullity.
Yeah.
Column
M into n. Yeah, m into n. Row into column. So C is the column. So total number of columns. So here 3 columns we have. And for example, here in this case, above case, for example, here what is the nullity? 1, 2, 3. So what is the, how many columns are there? 1, 2, 3, 4, 5, 6, 7.
3.
7. And what was the rank? 1, 2, 3, 4. So nullity equal to 3. Next. There are square block matrices as well, but that is not much will be required. We will be doing it in another way. So for even and odd, for example, but some determinant will be useful. Determinant of some special matrices, I could say. At the time of examination, it will be not only time saving but also conceptually very important. For example, alpha 0, 0, 0, beta. Okay. Then it is 0, alpha 0, beta, and 0. So you see, alpha is going and beta is also coming towards left. So in that way, so 0, so beta ऐसे ऐसे आते हुए ये beta हो जाएगा. Getting it clear? ये alpha होगा and this will be beta 0, 0, 0 alpha, isn't it? So what was the row and column? Alpha into alpha matrix, we can say it. Okay. Or rather say n into n कर देते. N into n matrices. So what is the determinant value? Can anyone guess here? It's simply alpha square minus beta square whole to the power total n cross n, so n by 2. Okay. We can also say that aij का अगर format लेंगे, ai is equal to alpha or beta or 0. ai is equal to alpha means I equal to j, means you see that if I equal to j, this is the value. Can you tell me in this format what when aij is beta? Anyone?
I plus j is equal to n plus 1.
Yes. If row plus column equal to n plus 1, for example, it is beta when it is coming. Beta is coming I plus j, row plus column. Okay. So this is a 1 into n format. So row plus column. So that is equal to n plus 1 in this case, directly we can say. So obviously from this format, actually we can find this. So this is the main key for finding, and otherwise it is 0. In all other formats. There is another special determinant formation we have. Okay. And remember that, is there any restrictions for n? Any restriction? Answer is yes. N equal to even. But what happens if n equal to odd? Then it is alpha square minus beta square into whole to the power n minus 1 divided by 2. Alpha square minus beta square whole into n minus 1 by 2 for, but what happens if we introduce, so if it is non-square, so then another value. So let me just write that thing, n equal to odd, so one extra column has to be there. Okay, let me just do that for you. So if it is alpha 0, 0, 0, 0 beta, then 0 alpha 0 dot 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 0 beta and 0. Okay, so in that way 0, 0, 0, and in the middle it will be maybe alpha 0 and beta dot 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 0, and then 0, 0, 0 alpha beta, so you can take it gamma and 0. So this is the special case. Then again after the release charge changing, okay, now beta 0 alpha, so they exchange their position in this. You see, they exchange this two, then this, and then dot 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 0, beta and 0. Zero beta 0 dot 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 0 alpha 0 alpha. Oh, come on. Okay, So this is a perfect format for this, and here the value will be as the way we have said. Okay, but you need to take a look into the format, then only we can proceed with it, the kind of thing like this. Okay, next one is the normal rank calculation, and all these kind of questions will be there in the examination. One particular question I can say you is it's from an IIT JAM question paper, JAM 10. They have given this question that P is a 50 cross 50 matrix. Okay, and Pij equal to minimum of I comma j, where I comma j equal to 1 2 dot 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 50. Okay, then what is the value rank of P? So,
50.
so P equal to, if we can find it. Okay, so writing the matrix is the only thing. So 1 1 dot 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 1. So this is the main key here. Pij equal to minimum of I comma j. Minimum of I comma j. So if it is a 1 cross 1 case, so what is the minimum? So 1, then 2 2 2 2 2. Then it will be 1 2 3 dot 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 3 dot 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 1 2 3 and 50. Okay. So this is the system. Now from this, how can you go for the rank? So if I do the very basic thing, let the first one be 1 1 1, there is no change needed. But if I do R2 minus R1, R3 minus R2, R4 minus R3, in that way R50 minus, or rather say keep it like all 1, R50 minus R1. So it will be easier for us to get a formation. 0 1 1 0 1 2 49. Okay, so in this case also finally we can get 1 1 1, this minus this 0 1 and 1 0 0 1. So again the correspondence rule needs to be applied, and 0 0 1 dot 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 48, and now so on. So here in this case we can see that the rank is, or here we can finish it off as well. So in that way, if we keep on going, so the last value will be still there, and we end up with a 1, but it means 0 0 0 0, so it's 1. So no 0 row will be there, so the matrix will end up as rank equal to 50. So the only thing is how many 0 rows will be there. Many of the cases 49 is also given as an option. It seems like the last time it will be 0, but the last row will be 0 0 0 0, and even the last term will not be 0. So that is the main idea behind these kind of sums. So you don't expect symmetric, skew-symmetric doing kind of a sum. So you can expect these type of advanced applications now. Okay, sometimes you can do it if you can remember those formats which I have told you. Sometimes without that format also you can do. So it all depends on the given structure, how quickly you can get a structure. For example, the complicacy of the question is the key. A is a n into n matrix, which is Aij, n greater than equal to 3, where Aij equal to bi square minus bj square. Then determinant of A is what? And remember that B, there is no restrictions. I and J are the restrictions only being put over here. So let's take here, if we can say that the options I can give you. Product of I less than J, Bi minus Bj. Option B, product of I less than J, Bi plus Bj. C, 0, D, 1. What is the possibility? So again, I'm telling you, is an n cross m matrix, normal matrix. There's no hanky panky business over here. Okay, so the hanky panky thing is happening in this portion. So try to figure it out. So this is the main zone of the question. Aij equal to this thing, and certainly they are asking the find the value of the determinant. Let's take okay. So what will be the matrix?
Sir, all diagonal elements will be 0 first.
Yes, good. Next.
So निकाल रही हूँ values अभी तो.
Aij is bi square minus bj square. You can utilize this bi square minus bj square. So we do 2 square 4. So this is minus 3, 8 minus 1 minus 9. So that is minus 8. Second one, this one is 1 minus 3 minus 4. And this is 4 minus 1, 3. देखिए ये तो इसका opposite ही आएगा. It's quite like a skew symmetric one. So if it is minus 5, so you don't have to calculate the rest of it. So this will be the thing. Now what is the determinant value here? Any guesses? 0, isn't it? Now determinant is not equal to product of bi minus bj. ऐसा तो हो नहीं रहा है. Neither determinant is equal to, not equal to product of I less than j bi plus bj. ये दोनों में से कोई भी नहीं है. And determinant of ab not equal to identity. So nothing is happening, only c is happening. Here. So in that way, normal determinant value calculation, just by forming this and taking any arbitrary value, you can do it for this MCQ. Especially these questions are designed in this way, okay, so that directly you can form it. The problem with our graduation studies books is they lack this thing, so that's why we have to do it. And unfortunately, there is no well-written book on this, so that you can directly do that. Okay, this will cover up everything. So I try to gather as much as possible. So best way is doing it from the past years. Okay, taking it all together. So all the eco, math, and stat, masters entrance examination together, you take and take the subjective questions and try to solve it. Whether it is mathematics optional, whether it is in the IFS mathematics optional, whether it is BCS mathematical optional. So these kind of structures together needs to be taken every time. So just go for a chapter and whatever examination you have, you try to solve. It doesn't matter what it is or what kind of thing it is. Okay. So every time we follow the trace, we get a different kind of a value. So another question I am trying to give you now, for example, J, let me be J. J is a 101 into 101 matrix. Okay. With all entries equal to 1 and I equal to identity matrix of order I equal to obviously 101 into 101. So the determinant of j minus I. Is it 101? Is it 1? Is it 0? Is it 100? Yes, Rahul, CSI and UGC NET examination also parallelly you can solve. They have a very good collection of questions. Any idea?
So 1.
1. Okay. Anyone else? Show me your workings also. Send it to me.
So actually I didn't do any working on paper.
Okay,
I
okay.
just followed it mentally only.
Okay. Can you say trace of J? Can we see? So if all the entries are 1, for example, 1 3 cross 3 matrix. So if all the entries are 1, so trace has to be 1. So trace has to be, sorry, 1 into 3. So here trace has to be 101. So there is no problem. What are the eigenvalues of the matrix? Eigenvalues of J equal to trace of J, comma 0 0 0 100 times. So this is 101 0 0 dot 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 0 100 times. Now determinant of now when we go for the determinant of J minus I, so that is they have asked, is nothing but the product of the eigen, isn't it? So determinant is nothing but the product of the eigenvalues. How many values are there? Remember that this is the eigenvalue of J. So what is the eigenvalue of J minus I? 100 minus 1 minus 1 dot 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 minus 1, isn't it? So here it is product of eigenvalues of this thing. So minus 101 minus, sorry, minus 101, I'm saying 100 minus 101 100 times. So 100 into 1, so 100. Unfortunately, your answer is wrong. So here we have to go for 100. Anyone are having any difficulties in understanding this particular problem? You can ask me.
Sir, more one.
Yes, sir.
Yeah, which one?
So tell me again, sir, this.
Yeah, sure. For example, we started with this thing. So they have given us a matrix like this. They said this is a 101 into 101 matrix. Okay. They can give anything. But one thing for sure, it's a square matrix. Okay. And all entries are 1. And suddenly they said that what is the determinant of J minus I? This is they said. Now, they could have also said J minus 4I. They could have also said J minus 100I. There is no problem. So first, in these kind of matrices, 3 things are needed: eigenvalue, trace, and determinant. So determinant is nothing but the product of the eigenvalue. So how to find the eigenvalue from the trace thing? So once the trace is coming, so trace of this thing and rest of the values are 0 anyway here. Now it is coming over here. So now you got the eigenvalue of J certainly. So they have given J minus I. They could have given J minus 100I maybe. So then the value would have been 101 minus 100 is 1, then minus 100, then minus 100 dot 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 minus 100. So this thing is 100 times j minus 100i. So this determinant of j minus 100i, determinant of j minus 100i. So this thing would have been the product of these eigenvalues. So 1 into minus 100, 100 times, isn't it? So here, fortunately, they have given it j minus I only. So minus 1 into 100. So 100 times minus 1 multiplied together. So this is 100 times, should have said. I have written minus 1 into 100. So minus 100 times. So that gives you plus 1 and into 100. So that the whole thing is gets up to 100. So here also, it's a positive value anyway. So 100 to the power 100. That would have been the determinant of this value. So j minus what, this determinant of what they are asking to find out, that is not important. The rest of the part is really important. Okay, so we need to focus on that. Okay, next.
So trace of J is equal to modulus of 0, the modulus of O.
Trace of the matrix is nothing but the sum of the diagonals. So we have 1 into 101. So 1 0 1. So it's like a matrix like this: 1 1 1 1 1, then 1 1 1 1 1 dot 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 1, then 1 1 1 1 1. So in that way, so all these things. So together this crosswise 1 plus 1 plus 1 plus 1 dot 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 100 times. So 1 into 101, that gives you the trace. Okay. And with respect to matrix, for example, always remember one thing. My personal take on this. For example, if you take an n cross n square matrix, okay, and if you see that BA plus B square, if you have a relationship like this, equal to I minus BA square, just like this, they have said it. So now what you can guess about the matrix? So things which you can guess about the matrix. Let's see. First of all, A and B are matrices. So BA equal to this thing. So you can just put it as a single equation number 1. So if A equal to 0 and B equal to I, then condition 1 satisfied. Isn't it? But in case A is singular and AB is singular, okay, then singularity of the given system is not ensured. Okay. And for example, here, how we check? We check with some arbitrary values. A equal to minus I, B equal to plus I. A equal to plus I, B equal to minus I, in that way. Okay. So all these cross checkings, all these different things needs to be done, and we can find out the value. Okay. So what is A plus B? What is A minus B? This kind of stuff. Usual stuff, but useful ones. Next, let's find out a relatively bigger question. Let's find out the rank of this matrix. 1, 1, 1, 1, and 1. Can you find the rank of it? Remember that do it only 1 line or 2 line and it will be done. Let me give you the options: 2, 3, 4, 5.
5.
5. Okay, that's a wild guess, but let's see whether we can reach it to or not. So if you just take it to the first thing, R 5 minus R1, R4 minus. So if I just say it like Ri minus R1, where I greater than 1. Okay, new style of writing. Ri minus I1, I equal to 1, 2, 3, 4, 5, anything can happen. Okay, so this thing is this. So obviously this will, in the very next line, this whole thing will become 0, isn't it? There is no problem. And this whole thing in this way will be becoming 1, 1, 1, 1, 1. Okay, this will become 1, 2, 2, 2. Let me just write it. 1, 1, 1, 1, 1. Sorry, 0, 1, 0, 1, 2, 2, 2, 0, 1, 2, 3, 3, 0, 1, 2, 3, 4. Okay. Very similarly, we can do it like R3 minus R2 now, R4 minus R2, and R5 minus R2. So in that way, we can reach to another part. So in that way, the lastly we can reach to this situation 1, 1, 1, 1, 1, and every time a single 0 is increasing. So lastly, still we don't get a 0 row, no 0 rows. So if there is an absence of 0 rows, so rank will obviously be 5. So in these kind of questions, our target is to find out how many 0 rows are there, and we go away with this. Okay. Next, now something different style formation I will be going, and I will be giving some special homework on this. For example, can you find this? This will be as a homework. 1, 1, dot, 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 1, and this is also 1. So all are 1. It's a 10 cross 10, and b equal to a by 10. So can you find b to the power? B4 whole determinant plus trace of b square. Give it as a homework. Take it as a homework, rather. Remember that it can be extended up to anything. But one thing for sure, whatever is there, this has to be in the denominator. So this is a formational question structure.
So can I take this A 1 1 1 1 with this 2 cross 2 matrix and then proceed this math?
You want to take it as a 2 cross 2? Yeah, we can, but in that way, this value is different, right? So this is only applicable for 10, so you cannot proceed like that. Okay. But yeah, you can give it a try. We will be discussing this thing in the next class.
Okay.
For example, if person A wants to get married to person B, but person B wants to get married to person C, person D gets to married to person D, D marries to one to E, F, G, H, dot, 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 Z, and Z wants to get married to A. Okay. So we have managed to complete the circle of marriages here. But the biggest problem is that there is no marriage happening, right? So with respect to A, A wants to get married to B, but Z wants to get married to A. But whether A wants to get married to Z or not, that we don't know. Okay. And remember that what if multiple marriages are possible? Okay. So A can get married to Z and A can get married to B as well. So in that case, can you guess the total number of marriages? So this is another linear algebra question. You know that linear algebra में अगर सोचा जाए number theory, advanced number theory भी आता है. Okay, in advanced group theory में भी ये आता है, where we will be learning pigeonhole principle. Okay, some advanced combinatorics and all. So again, let me repeat, A, B, C, D और ये alphabet की तरह है, Z 26 तक है, ठीक है? So let's just have it like an English alphabetical rule. So all these letters want to get married to each other. A wants to get married to B, B wants to get married to C. And obviously this is one-way traffic. It's a one-way traffic. So B doesn't, A wants to get married to B, but B is not. So otherwise there would have been a marriage, right? So in that way, Z, but Z is the, and Y wants to get married to Z, but Z wants to get married to A. Otherwise we cannot complete it, right? So Z को भी तो किसी के साथ शादी करना है. So that's why intentionally this Z with A comes in. Because Z cannot get married to Y, he doesn't want to, but he wants to get married to A. So A has a possibility to get married with Z, and if B agrees, but A wants to get married to B, but B doesn't. So can you tell me how many marriages are there? And if multiple marriages are also possible? Anyone?
So in multiple marriages, if Z, so Z gets to marry A and B, like only two people, not other than that. वैसे दो का पेयर में लेना है, मतलब इसमें ऐसा नहीं है कि अगर Z A से कर सकता है, B से कर सकता है, तो C से भी कर सकता है, मतलब मल्टीपल में तीन तीन के जैसा है, लाइक, या फिर सिर्फ A B या C D, like something like that.
Yeah, the biggest problem of this problem is we don't know whether C wants to get married to L. If C wants to get married to Q, what is that thing? C wants to get married to D, that we know. But, and she is not, she doesn't want to get married to the, मैंने क्या बोला, reverse नहीं जा सकता. So you need to listen to the inner parts in linear algebra very, very properly. No one can go reverse. So that means आगे तो जा सकता है. C wants to get married to D, so obviously she can get married to E or F. Okay, so that is the logic you need to find out. It's quite like, we call it in advanced mathematics, we call it a free left turn rule. Anyone know what is a free left turn rule? Free left क्या होता है? What is a free left? Any idea? मान लेते ये एक क्रॉसिंग है, ठीक है? सिग्नल का है, यहाँ पर आपका सिग्नल है, अगर आप इस यहाँ पर अपना बाइक लेके खड़े तो यहाँ पर आपका सिग्नल दिख रहा है, जो इधर से आ रहा है वो सिग्नल यहाँ पर देख रहा है, जो इधर से जा रहा है उसका सिग्नल इधर को है, और जो उधर से आ रहा है उसका सिग्नल इधर है, ठीक है? ये चार सिग्नलिंग पॉइंट है. तो आपके लिए आपको कहाँ जा सकते हैं आप? आइदर इस वे और इस वे या फिर दिस वे. So as in our Indian roads everyone keeps to the left, so if he goes, if this person takes a left turn, so he doesn't affect any of the riders because these riders are coming in this way anyway, and these riders are coming in this way, but in the right turn left turn there is a restriction, okay, coming this cross. So in Indian roads, in many of the roads there is a free left turn. मतलब लेफ्ट टर्न के लिए देयर मे बी अ रेड सिग्नल हियर, रेड सिग्नल हियर. रेड सिग्नल किसके लिए है? राइट टर्न के लिए रेड है, सीधा जाने के लिए है, बट लेफ्ट टर्न के लिए फ्री लेफ्ट. ओके, सो यू कैन गो. ऑब्वियसली रिवर्स जाना इज नॉट एन ऑप्शन. नाउ यू आर गेटिंग इट. रिवर्स जाना ऑप्शन में नहीं है, तब आपको यू टर्न लेना पड़ेगा. So with respect to real life, how, what is the possibility, and in these calculation wise, and with respect to entire day में how many traffic are there, what is the timing of the day, what is the season of the day, all these calculations से decide होता है कि कितने सेकंड के लिए इस रास्ते में रेड सिग्नल रहेगा या फिर ग्रीन सिग्नल रहेगा. ओके, सो दिस इज अ वेरी कॉम्प्लिकेटेड सिग्नलिंग सिस्टम एनालिसिस. ओके, सिग्नल सिस्टम बोल के इंजीनियरिंग में एक टॉपिक ही आता है, एक पेपर भी होता है. इट्स वेरी वेरी इंटरेस्टिंग टॉपिक. वन ऑफ माय इंजीनियरिंग फ्रेंड्स, we just love to discuss all these things. लेकिन अभी के लिए आप ये समझ लो कि it's a मतलब why this marriage ceremony thing comes in, just because of this thing. So you are not allowed to go backward. So A is never going to get married with Z. Okay, so for A में Z पे ये इसे वापस आना पड़ेगा. So for A he can get married to B, C, D. So there are how many options are there? Please tell me. In that way, you can see that A this wise Z tak ja sakta hai. Okay. A in that way, A can go to forward, so A can get married to Z. And Z anyway likes A. So one sure marriage is A to Z. That's one sure marriage. And obviously A can get married to B, B, C. In that way, A has 25 options. Or 24 plus 1. B has 23 options, isn't it? B can get married to Z. In that way, we can add it and we can get a series. Okay, so in this signaling system also, if the free left turn is being allowed, so how many, what is the average waiting time? So for that, har ek signal, har ek timing, ye sabhi kuch diya rehta hai. And by calculating that, Google tells you, ये कौन calculate करता है आपके लिए? रोज calculate करता है आपके लिए Google मैप में कैसे बोल देता है कि 45 मिनट्स ही लगेगा, और चाहे आप जितना भी जोर से बाइक साइकिल गाड़ी घुमा लो, अब ये 45 के आसपास ही पहुंचते हैं। अगर आप वॉकिंग में जाएंगे तो भी जो टाइमिंग देता है, और ये स्पीड में जाएंगे, वॉकिंग का फिर भी मैच करना थोड़ा मुश्किल होता है, बिकॉज एवरीवन्स वॉकिंग स्पीड इज डिफरेंट। बिकॉज इस रास्ते में आप जितना भी स्पीड में जाओ, इन नॉर्मली देखा जाता है कि नॉर्मल रोड्स में स्पीड होता है 20 से 25 में किलोमीटर पर आवर। अब आप कहेंगे मैं तो 60 में चलाता हूँ सर, डजंट मैटर, आप एंड ऑफ द डे कितना रुकते हो, कितना करते हो, मतलब 1 घंटे में आप 20 किलोमीटर ही कवर कर पाए। इवन इन द हाईवेज 35 to 40 इंडियन हाईवेज में रहते हैं, एंड दिस इज कीपिंग विदाउट, एंड ये 35 to 40 ये मेरा कैलकुलेशन है, डोंट टेक गो फॉर द गूगल, ठीक है, क्योंकि इसमें हॉल्टिंग रुकना, ये थोड़ा सा स्पीड कम करना, कभी कभार बाहर देखना, so this is an average of mine, and I think it is applicable more or less to everyone until unless you are a super biker. Okay, so this is a rule of average in the space we try to do. So now we enter into the world of vectors and their spaces. Before that, let me just tell you another important stuff of the linear algebra. So what is the space is all about? Can you think what is the space? Space है क्या? मान लेते एक फील्ड है, लेट देयर बी अ फील्ड। ओके, फील्ड के साथ मतलब फील्ड को ऐसे लिखते हैं, प्लस एंड डॉट प्रोडक्ट का दोनों ही। सो द एलिमेंट्स ऑफ द फील्ड, फील्ड का जो एलिमेंट रिग्रुपिंग फील्ड किया ही था, सो बेसिक किया था, एलिमेंट्स ऑफ द एफ कॉल्ड द स्केलर्स। ओके, लेट अब वी आ गया, मान लो एक नॉन एम्प्टी एक सेट है, वी इज अ सेट which is non-empty. Now the elements of these are called vectors. So V is the vector space over the field F. If now the following conditions we need to think about. ये हर बार condition दिया जाता है. So if there is an internal composition of V with respect to addition, there is an external composition of V with respect to scalar multiplication, and there are double compositions as well, so different kind of thing. So we are trying to check, it's quite like, again, if we go to an example of February, okay, the upcoming month. So in February, for example, if we take a 14 February as a date, so everyone know it as a Valentine's Day, day of lovers and all. Okay, so now if we think that before, what is the probability that a person will become, will get a girlfriend before 14 February, or what is the possibility that you will get a boyfriend before a 14 February? So this is dependent on some different factors, but remember that this is on the same field whether you are or not. Okay, so the field is based on a space, and here two spaces. The geographical space is also there, because you are not going to get a girlfriend from Romania all the way. Okay, that's not possible. Or you are not going to get, and if you get it, so there is a time frame as well, that is 14 February. So if I consider from 26, so there is only 18 days left. So within these 18 days, you have to do something wonderful in order to get it. So time frame and geography. So two frameworks I have provided. Now there is a study and examination for you guys. or someone is doing jobs. So this is a third propaganda is coming. So now if I keep on introducing different kind of formations into this vector space, so things become complicated. Normally we can say it v1 plus v2 is a pass of the vector space where v1 and v2 separately are here. So it is easier for us. Now here we have to do it for v1 and v2 dot 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 vn for this. Now to make sure that everyone is a part of this vector space is important. And now after that, even if happens, what happens, there is a subspace there. Okay, now all these things, like for example, A meets B. Very simple, right? But this depended on infinite possible factors. What happens, A उस दिन घर से निकलता ही नहीं. What happens, B उस दिन घर से निकलता है लेकिन कोई दूसरी जगह में चला जाता है C के पास. Okay. What happens if there is a rain? What happens if there is a very chilly weather and B doesn't want to get out on a chilly weather? So there are many things, and after that all these things matches comes in, then only there is a perfect match. So every day on a daily basis on our space around us, we can see infinite number of matches are not happening. And only a very finite number of matches are happening because of only one reason, that the space gets bigger and bigger and bigger. Okay, so if we talk about another thing, what is a convexity of a set structure? So if I see that, if I take 2 points in a set, okay, in space rather say, and they can be joined by a line, and the line is also within the space, there is no problem. But things become complicated if I still get a point on this. I can join it, but these 2 points we cannot join. This is outside. Okay, so we cannot say that 2 points cannot be joined and the straight line within them is also in that space applicable for everything. That is not, we cannot say. But we can say that in some cases. Now that's why the problem occurs. वहां पर v1, v2, it is easy. Any 2 points is marked out. So we say this is by v1, v2. इस 2 पॉइंट के लिए तो ये हो गए. But now if I have it v1, v2 and vn, so one can go to 2, 3, 4, again go to that marriage example. One can go to v2, v2, vn. 2 can go to again 3. One can have this option is 2, 3, 4, 5 dot dot n. 2 can have this option 3, 4, 5 dot dot n. 3 can have this option 4, 5 dot dot n. 4 can have this option 5, 6 dot dot n. In that way it keeps on going. So with respect to every new formation, although the one option is becoming less, but it is still a very big calculation. So field of study, and then comes the biggest problem, as the complex number structures are coming. Okay, so why complex numbers are very much handy over here. For example, you have a plane like this, you have another plane, and you see that the intersection of these 2 planes can only get you to that solution point. So you think that, okay, let's create a line like this, or let's create a line like this. So on an imaginary plane, you are making them intersect to each other. So that creates an existential inversification rule or inversification phenomenon. So how in real life happens? So for example, there is a Sri Lanka is under a debt crisis. Sri Lanka has taken some money and keeping some of their biggest of the like airports and all as a collateral to the Chinese government. And obviously, according to the rule, they have taken like $1 billion, and now it is becoming 3, 4, 5, so huge amount. So obviously they can't pay it. India is giving them some amount of money and whatever it is. Okay, so this is associated with this. Now what happens? What would be the decision of India under this thing is associated with this space? Well, India can do things. India can repay the loan for them now, and take control of this space. But again, there's an international territorial rule which may not allow them to do that. And if it is on a good faith only, they do it for Sri Lanka. Sri Lanka may become allies with respect to some other countries with which India doesn't have a good relationship. So, for example, if I talk about a very special country in this case, although in a maths class we talk about different things, but Bhutan is a very special country which doesn't have any extraditional treaties with USA and even India. Okay, so you can talk about this thing. So if we take India as a space and Bhutan and Nepal as two close ones, so Nepal has all the kinds of treaty and Bhutan has almost no kinds of treaty, and it is connected with most of the places in Chinese economy as well. Okay, so in a very complicated way, who is actually friend of which country and will maintain their friendship, it is not possible to guess, and we need a very complex structure for this. So that is a vector space actually. Okay, so I tried to make it as complicated as possible, and I ended up making it one. But remember that existential, why we need this, why we need this vector, that is the main thing. So हर बार क्लास में क्या होता है, सर आके लिखते हैं u v w is r square, so u plus v, so u plus v and w is u dot vw, and u plus v plus w. So changing the brackets, what is this thing? So why we are changing the bracket and something? Obviously we know if 1 plus 2 plus 3, 1 plus 2 plus 3 and 1 plus 2 plus 3, it's all the same. So why all this is associativity becomes very important. So associativity with respect to these kind of country, we can say countryship, can create a magic. So we will be going with this in the next session of linear algebra, which will be very important, where we'll be utilizing a lot of inverse rules in order to find it out. And that way we will be entering into advanced modern algebra as well. So keep it a little bit as cool as possible for the next session. And in the meantime, there is not much of a homework, so you can practice it from the different question papers, where basic matrix, eigenvalue, eigenvalue, even eigenvector, you will be able to do. Determinant application, properties of matrix, skew-symmetric, Hermitian, skew-Hermitian, these kind of things are discussed. So you can have a look into that and send me your trials. And in the next class, we will be finishing, not finishing, but we'll get into the serious segment of it. Okay, that's it for today. And those who have